minutes every 30. So those will just be the data points when you go back into the video and look at it, just at those times. See what the dial's measuring. But, all right, so you guys ready? Video's going?
Video's going, yeah.
All right, cool. So I'm gonna put it on. 3, 2, 1. All right, and then now for post-lab stuff, you're just gonna make a graph of those times and what the elongation is, and then you're gonna use this formula here. So the load that is currently in the system, the gauge length that you initially started at, your cross-sectional area of what you're measuring, so that's the width and the thickness measurements that you guys took, and then the Young's modulus of it, and that will give you your strain. And you'll just do a pre and post to see, like, at the end when you remeasure your gauge length, how much has changed, and then you're just going to tell me from that how much will it be changing per hour. So, yeah, it's really this is the easiest one.
Pretty much changes per hour.
I know.
The hardest part about this lab is just waiting.
The longest part is just going to be going through the video and
Just finding the times, writing down those numbers. And
how long does it take for this one to?
usually it's about 5.5 minutes for each specimen. So if things go well, hopefully you guys will be going by half an hour from now. Get out of here and go enjoy the rest of your day. So, we don't have any markers up here, do we? So, hopefully this is not important stuff. So the two graphs you're going to get one for the HDPE and one for the lead. The HDPE should look something like this, and the lead should look something like this. So the lead's a little bit weird, and in that, like, as soon as you put the weight on, it starts, and this is the time, and the other one should be the strain. Yeah. So it experiences a lot of strain really quickly. Hits a point where it's like the dial somewhere in the middle of the video, you should see it's just constantly moving at the same rate. And then once it gets down like really close to the bottom, right before it's about to break, it'll experience that like jump at the end. The HDPE, on the other hand, is very much, it experiences a lot in that first section, and then it just kind of tapers off over time. Just because this is actually the stronger of the two materials, which is weird because you think usually a metal would be stronger than plastic. I guess this is the other way around because lead is so soft. So that'll basically be your post lab, is make those two graphs, tell me about the strain, and then tell me about how the strain moves over the course of an hour. And it should be something like 0.02 inches per hour or something. It's a really small number. Did it go? Done?
Yeah.
Oh shoot! Alright,
Or
cool.
almost.
It's done.
Okay. Yes.
That was fast. Alright, so I'm gonna move that out of the way. That was a lot faster than it should have been. Weird. Alright, so now you guys get to take measurements. Oh, I see, that's why it looked like it was about to fail there. So when you do your measurements, if you can, try and get right at that point where it starts to tick a little bit, because that'll be your most accurate in terms of the strain point. While you do that, I'm going to load this guy in.
Here and here, so the moment is going to be negative. with this value,
Okay, so gauge length is 2.551.
5 minus 5. You do the same from this end, which is 38.
The new width is 0.144.
So this is the point B, point A. It's going to go like
0.144, yeah. And then thickness
Here and here,
is
if you take another section here, do the same analysis, you will see that the bending moment is going to be constant between here and here. So it's going to go like that. So that's minus.
0.04.
Okay? So that's your bending moment.
0.040, yeah.
So that's the theoretical bending moment. So if you apply 1 pound load,
And just as a check,
moment
gauge length
is going
increased,
to be here.
Yes.
the width and thickness decreased.
Yes.
Alright, means you did it right.
The moment is constant between.
Alright, one down, one to go.
Strain gauge is allocated
Yeah. it's
Video still
running.
going?
between the
Cool.
Is it in?
Yeah.
Alright, so same thing as before, is this zeroed out? I tried to, I'm not sure if it's exactly on it.
Any questions? Alright, now,
Good now.
we get the bending moment also
You ready?
from the strain gauge reading by using the
That-
formula.
That didn't change
We
the
have
dot,
not
did it?
studied
No.
yet, so
Okay,
I'm
cool.
gonna put that on.
Alright, 3, 2.
This is the bending stress sigma.
There's one other thing that might be important.
MC or I.
Are those numbers there? That's technically preload on the system because the arm has a weight, these pins have a weight. So if you want to include that as well, it doesn't change your numbers too much, but it's up to you guys. Because is this your formal?
Yeah.
Okay, you might want to include those
Yeah.
numbers then too.
Just take a picture of it.
Yeah.
Elastic reach.
Any other questions about what you're supposed to be doing, how this all works?
So we just add that to the tool.
Yep, that's the deal.
You're gonna measure this.
Because technically it's being restrained by that amount.
Young's modulus for steel. This is made of steel.
It doesn't actually do anything because it's not enough weight to actually reach the point where it's starting to deform. But
I is what's known
count
as
it
the
if you
moment
want.
of inertia of the cross section. So that's the cross section. You have measured the width and the height. Okay. I is given by B, H, Q, and C is the distance from the neutral axis, the middle of the beam, to the edge. C.
What do you guys think of the other
1
labs?
half of it. Okay?
Out of curiosity, which one's your favorite? Not which one's the easiest.
Thickness.
Which one is your favorite?
Now go ahead and turn on the.
I actually like the tensile test.
So we have connected
Yeah.
the strain gauges to a Wheatstone network.
In this one here.
Okay, the resistance of this strain gauge is 120 ohms. So one of these is the strain gauge, the other 3 legs are standard 120 ohm resistors.
Are you guys all juniors?
So when they are in balance, that means all the
Sophomore.
resistors
Are you
have
in
the same
aero club?
value.
Huh?
Are you in
Voltage
aero or
across the
mech?
terminals will be
Civil,
zero.
oh, okay.
When you apply a strain,
And really civils have to take mecha-solids. It makes sense.
top
That was
5%
just
will
aero
be
and
extended,
mechy.
so the wires in the strain gauge are going to be stretched.
I don't know.
So
I'm
this
just
is going to increase the strain gauge, diameter is going to decrease, so there will be a change.
I'm also
in
learning it as I go.
Increase in resistance, and that is calibrated to reach strength. Now, these are reading some funny values. You want to zero them out, hit a balance. Hit again balance.
We just do 10 minutes of video and find all the
Channel 4,
different
nothing is coming
Oh.
out.
That's the worst part about it is just
Yeah.
going through finding the times.
When I was reading it, I was like, and I saw that, I was like, are we gonna do that? I thought it was gonna be a computer that did it. Alright, sweet.
So now go ahead and
That's
add.
all.
Didn't think I'd have to take a video.
500 gram.
The first group they did it, tried doing it by hand. So
Yeah.
like, have a stopwatch, read out the times as they were happening, and try and also match that with the dial as it was moving, and try and get like as precise as possible. And then the second group's like, just take a video. That's not like, it's like, yeah, that's not smarter. I like that method
You
better.
can see, this is connected to channel.
Makes it easier for you guys at least.
Yeah.
There's not one person trying to read out the times, one person calling out the measurement, one person typing it in or writing it down.
Yeah.
Especially for every 5 seconds for the first minute. It's a little difficult.
Yeah. And you're almost guessing.
Make a table and say load.
Yeah. You have to like get to the closest like 10. You can't really get the individual little increments.
So some of the specimens failed during some other testings?
Mm-hmm. Yeah, so this one ended up failing. I think this is the only one that failed so far. It was one of the Thursday courses had that happen. Usually they just get, let's see if I can find one of the good ones. They might have thrown it away. Yeah, no, here. It's like this one. You can see it got really, really close to the point where like you started to see the color change because it was just about to fail.
Not quite like that, but
Yeah.
you could still tell.
Yeah, you guys got a strong piece. In terms of, or I guess, flexible. Lots of stretch. But again, usually it takes about 5 minutes or so to get there. For yours, for it to be only like 3 minutes was pretty quick. And like these guys, usually you don't really see anything on them.
Another 500.
They have a lot more ability to return back to normal. So they're stretched. They're definitely stretched, but
All these have been tested already? Oh, wow.
but you don't see the same sort of deformation in the actual like material surface.
Plastic.
But they are in
plastic.
Yeah, exactly. Exactly.
Oh, crap. I think you can still see it. Plus we're at 5 minutes, it's every 30 seconds. So this did elongate?
Mm-hmm. Yeah, all of those have been tested already. So you can see clearly the difference between lead and HDP. In terms of one, just the amount it stretches, and two, the actual like surface. Alright, is it done? Let's not quite done yet. It's getting close though. I give it another 15 seconds or so. You'll reach the bottom.
Maybe one more, you know, the little one.
Alright, so it looks like you've hit. So you're done. That's that. So just get your last measurements on this piece.